So, what is systems design? Or for that matter, system identification. Identification means you're already looking at an existing system. Design means you're starting from the scratch. That's all. So when we look at many things that are around us, we realize that they have been designed, they have been made to suit a certain purpose. So at that stage of design and probably the first level of manufacturing, there is a need to examine the limitations of any design. How far will they go? Will they satisfy the requirements of a design? For instance, a shaft may be designed to operate at 1500 RPM. So taking into consideration factor of safety and everything, you may want it to be safely operating at least up to 3000 RPM before it fails. So we need to know when things will start to fail, when they no longer operate within the requirements that have been set aside for them. So we need to look at something that resembles the original system. Take, for instance, the case of an aircraft or a car or a motorcycle or a shaft even that we just now discussed. All of these things are quite expensive. To manufacture a shaft to within a tolerance may cost sometimes thousands of rupees, depending on the accuracy within which you want it made. So we need to find a way in which we don't keep on testing things to destruction, because that can become a very expensive habit. Please bear in mind, testing things to destruction has its place in engineering. We are chronologically much further ahead in the line before we start to test to destruction. Test to destruction is something that's done probably after the design is finalized. Then we take one or two or three prototypes and put it through the entire process to see how it works. So we need something like the original system that can be reassembled instantaneously if it fails, or one that does not cost much to run thousands of times. Obviously, a computer program is one that fits this requirement quite well. There are many applications that will test, but how do they write those applications? Well, to write those applications, the first thing we do is to design that system using mathematics. So we need something that behaves close to the real thing and gives approximate answers, not necessarily accurate answers. It's enough as a first cut. It tells you, for instance, if the RPM required for the shaft is 1500, if your design and computerized testing will tell you that it will not fail up to 3000, you have a factor of safety of 2. So it's really what you wanted to do has been done. So the answer that you get from these models that you create using mathematics that designs the system is probably a first step approximation. But with that first step approximation, you can start fine-tuning your mathematics more and more, depending on how sophisticated you want to go, and in the end get more and more accurate results. So if we look at this simple graphic, it shows a system which is shown as a rectangular box, and this consists of whatever it is that has been designed. To this, one gives an input, and based on the input that's given to that system, one gets an output from the system. In the case, for instance, of the ceiling fan that we all have in our houses, the system may be the ceiling fan. The input may be the supplied voltage and current at a stated frequency. The output is, of course, a rotating fan. Now this is known as the forward loop. Input, system, output. From this, one observes either the fan is going too fast, maybe this is winter, you're feeling cold, or the fan is going too slow in summer, the breeze generated by the fan is not enough for you. This act of observation and coming to conclusion and consequently taking a corrective action is called feedback. So you compare the input. If it's going too slow, you increase the regulator position on the ceiling fan so that it starts rotating at a higher rate. If it's going too fast, you reduce it to get a lower rate. So, system is that which we wish to test to verify if it has met its design parameters. This is the thing that connects the input and the output. Without the system, the input and output have no meaning. It takes the input and it transforms it into the output, like we just explained in the case of a ceiling fan. The input is the power supply. The output is the rotating fan. So far, we discussed the open loop, or as we called it, the forward loop path. There is also feedback, as we explained in the case of observing whether the fan is going too fast or too slow. So feedback essentially is a corrective action in its most fundamental sense. You're driving a car, you feel you're going too fast, you ease off the gas pedal so that your speed comes down, or you press the brake lightly so that your speed comes down. This act in the case of ceiling fan of looking, feeling the rotation and acting accordingly is called feedback, and it generates the corrective action. What is the corrective action? It is to adjust the regulator. The regulator may be at position number 4 out of 0 to 5. And depending on whether it is too fast or too slow, you may go to 3 or to 5. So you are doing an incremental correction. So sometimes a feedback signal is also called error signal. If you are more comfortable with other types of example, one very, shall we say, funny example is the real life where we learn from experience. That's one form of feedback. So let's update that figure a little bit. So the system here has got the motor and the blades which is hanging from the ceiling. The input is voltage, amperes at the correct frequency, AC power supply. The output is the RPM of the ceiling fan. We observe the output. We take a decision on whether it is too fast or too slow. Correspondingly, we either decrease or increase the switch position using the regulator, which is the corrective action. So from this, some things are very obvious. The input is a one-time input, but continuous. You don't tamper with it after it happens. But when you change the position of the regulator, you are tampering with the voltage and the current a little bit. So these are all incremental corrective steps. So having looked at all this, why must we model? We have already gone through this once. Modeling, for instance, something like a ceiling fan. If you're going to make your own version of the ceiling fan, it will probably cost you a few thousand rupees to have a shaft designed, a motor made, mount a condenser above the motor, mount the blades to the motor. And in order to get statistical reliability on your results, you may have to make some few prototypes. All of this exercise becomes expensive. But on the other hand, if I can model the ceiling fan inside my computer using a differential equation that takes into account the rotation of the motor and the resistive powers that motor will feel in trying to rotate and the externally supplied power supply, and generate an answer for the resulting RPM, then I have created that ceiling fan inside my computer. So I need not waste time, money, and effort trying to create some 10 prototypes costing totally about 20 or 30,000 rupees, which I will, of which at least one or two will have to be destroyed because they are no good. So the prototype evolves with corrective action from the designer's side. But if that corrective action can be done to the computer, it is just a matter of resetting some parameters and running the program again. So fundamentally, modeling saves lots of money. It also saves lots of time. I can change, if I find stainless steel as a very expensive raw material, I can change it to aluminum by just changing the parameters such as Young's modulus. That immediately changes the material of the part that's being made. Consequently, my expense drops, but the whole thing takes me just about 1 minute to change. On the other hand, if you have to make prototypes and test it, it may take weeks. There are some basic assumptions involved in modeling. Some of them are natural laws. For instance, if you create a model where the model is getting better, where the natural laws are being violated, where you don't take cognizance of entropy, well, that is not much of a model. For instance, to design a model where the moving parts have zero friction, well, it's a good starting point, but it cannot be sustained in reality. Similarly, I'll have to worry about conservation of energy and mass, and or mass, because energy and mass are often interchangeable. A classic example is starting out a journey with a full tank of gas in your car. As you go from point A to point B, the fuel is being used up and it's being converted into energy, which in turn moves the car and its occupants from point A to point B. So by the time you reach your destination, you have less than half a tank of gas left. The overall weight of the car is less, but you have done plenty of work. There are also phenomenological laws to consider. Phenomenological laws are those which are as true as the sun rising in the east, but cannot be proven theoretically. Classic example is Ohm's law. Ohm's law can be verified but never proven. There are various forms of Ohm's law, such as Fick's law and Fourier law, which I'll leave it to you to Google and find out what they are. And very often you will come across situations such as this. For instance, can you prove Newton's first law? And just as a curious aside, Newton's first law has been around since Galileo's time, which is a couple of hundred years before Newton. But it's nonetheless been valid all this time. Having led conveniently into the topic of Newton's laws, let's also understand that these topics are being brought up for the purpose of refreshing your mind of concepts that have been dealt with long ago in class for you. Newton's first law simply states that unless acted upon by an external force, a body at rest or in motion continues to remain at rest or in motion, which means unless acted upon by an external force, the body is moving with constant velocity, which leads conveniently into the second law that says the externally applied force is equal to mass into acceleration, which directly indicates that a non-zero acceleration implies the existence of a non-zero external force. And the third law simply says that every action has an equal and opposite reaction. The concept of point mass here simply assumes that the entire mass of the body, regardless of its length, width, or height, is concentrated in its center of mass. If you are looking at a beam or a shaft in motion, we are only looking at the entire weight of the beam of the shaft, which may be 1 kilogram, and it may be 1 foot long by say 3 inches in diameter, but we are still looking at the entire mass of the shaft acting only on its center of mass. This is known, this is not only known, it works only in the case of totally rigid bodies. If the body has flexibility, then different parts of the body will start moving differently. So a point mass, which is a highly Newtonian concept, works only in the case of totally rigid systems. Taylor series and Maclaurin series. Taylor series and Maclaurin series are well established. It would be very useful for you to spend about 15 minutes of your time going back into your mathematics textbook and refreshing your mind about Taylor series. What is so great about Taylor series? Well, any function that you are given as representing any particular behavior or performance can be broken up into its constituent parts, like that is given on the slide. If it is within, if the function is valid within a range of p to q, and if some point a lies between p and q, then the function evaluated at a is given by the expression that's given here. So as you can see, the function is differentiable, the function is infinitely differentiable, and the function is given in terms of its derivatives. Zeroth derivative, first derivative, second derivative, and so on. When this a is at the origin, what you get is called the Maclaurin series. And we see that similar to Newton's second law, Taylor series is also one of the more useful tools in modeling. For instance, in the case of linear motion, if you're going to express something in the case of linear motion, this is just the position at that point in time. This is the velocity at that point in time. This is the acceleration at that point in time. If there is a third derivative, it would be the rate of change of acceleration, and so on and so forth. When you look at a mechanical system, when you look at it totally as a functioning system capable of accepting an input and providing an output, there are certain aspects to that mechanical system which are very obvious. The mechanical system has a mass, consequently it has an inertia. So in order to move it, or in order to change it from present course of motion, one needs to apply an external force and overcome the inertia of the system. So mass is a compulsory aspect of all mechanical systems. The second is that a mechanical system such as a shaft or a beam will have a certain degree of flexibility. If you apply so many kilograms of force, it will bend, flex so many inches. So there is a certain stiffness associated with the system. Third is there will be some loss in the system. Whatever work you put into the system cannot be taken out as displacement. Only less can be taken out as displacement. Let me explain that concept, if you will. If there is no loss in a system, if you set a spring to oscillate, it will oscillate in perpetuity. It will never stop. It is the losses in the system that make a spring stop. This is what we call entropy. This is what we call friction. This is what we call drag. These are all only associated with motion in mechanical system. So we have so far identified three components of a mechanical system: mass, stiffness, and loss, unrecoverable loss. A mass is modeled by us often as a point mass. Then it has no physical shape. That makes it very convenient. If it has no physical shape, you don't have to take into consideration various things that are happening. For instance, if I have a shaft 1 foot long and the origin of my coordinate system is located at the left hand end, and at the right hand end, if I apply a 1 kilo force, If I'm using a point mass concept, I can shift the point mass right to the center of gravity of the object. I don't have to worry about the couple or a moment that the point mass may create, the force may create at the center of gravity of the system. So these are all idealization and approximations. But as I pointed out earlier, modeling is an approximate activity to begin with. You start with reality, take a look at it, you simplify it till you can manage that simplified reality. And from that, you extract answers. Obviously, since you simplified reality, your answers are going to be approximate. You cannot expect accuracy from simplified reality. Stiffness, the classic example of stiffness is the amount of force that it takes us to bend an object over a certain distance. If you're holding a beam of wood made of cross-section 1 inch by 1 inch and it's 1 foot long, you hold one end fixed and press down on the other end. The other free end may flex by about an inch. For a 10 kilogram force, it flexed 1 inch. So the stiffness is so many kilograms per inch. So for each and every mechanical object, there is a stiffness which can be computed. For point mass, it becomes simply the question of dividing the required amount of force to produce the required amount of deflection by the deflection itself. For non-point mass, it becomes something a little more complex, which we'll look into later. In the case of energy that is lost in a system, friction, air drag, or just standard examples, there are different ways of modeling such losses. Most of the time, velocity-based model provide us with adequately accurate answers. Newton's laws are often taken on faith because fundamentally when we look at Newton's laws, it is the external force that becomes more and more relevant. You are looking at a body which is already either doing something or sitting at rest. Unless you apply external force, there is no relevance to Newton's laws. Because a body sitting at rest is just a trivial solution. So if you want to get something to move, you apply force. You want a very good example of that? Think in terms of how much effort it takes one to study. It's not that easy. A car at rest is nothing more than a pile of rusting metal and aging plastic. But a car that is moving has a lot more interesting things happening. So let's just start by modeling a very simple system. A ceiling fan or a motorcycle. Let's take a look at a motorcycle. We can reduce the entire mass into a single point mass. The shock absorber, the tires put together form the stiffness. The metal structure of the motorcycle forms a stiffness, the chassis. The air resistance forms the drag to the motion. So you get less displacement out than the energy that you put in. Now, one of the most useful aspects of modeling is what we call principles of superposition. Simple of superposition is very easy. As long as things are linear in a system, there is no nonlinear behavior. Then if an input A produces a response X and an input B produces a response Y, then an input A plus B produces the response X plus Y. Knowing the two independently is equal to knowing the two combined. Any function that satisfies the superposition principle is called a linear function. Very, very simply put, superposition is defined by additivity and homogeneity for scalar functions. The finished model, as defined just now, is the sum of its component parts, providing the linearity assumption holds. How real is such a model? We talked about modeling a motorcycle using a very simple mass, point mass, a stiffness, and a loss model. Well, it is quite real because it's possible for you to predict the response to situation using a model which will if the weight and the stiffness and the damping are taken accurately, it's possible to get a model which will probably be 85 to 90% accurate. Once you find it's 85 to 90% accurate, you start adding finer aspects to it, and the systems become more and more and more accurate. You may get even up to 95, 96%. Very hard to get higher than that because you start approaching reality. What can we model in this world? We can model just about anything: cycle, ceiling fan, a ship, cantilever beam, thermodynamics process, electrical circuits, lunar lander, heating or pumping water, pushing a heavy object. There are so many things. Just about everything in real life, economics, traffic, anything in real life can be made into a mathematical model, providing we understand what is happening accurately. We will look into the question of linear versus nonlinear a little later. I have used these two books in the process. In addition to these two books, you will also require mathematics book. I would recommend my old faithful Kreyszig, Engineering Mathematics by Kreyszig, and the Mathematical Systems Theory by Olster and Van der Voort is one of the best books I know, and I've tried, for the purpose of your convenience, I have tried to stay as close to the outline of the book as possible. Thank you.